In the previous lectures, we have been considering idealized components which can be expressed in very simple terms, very simple differential equations, that is the equation of a capacitor or the equation of an inductor or the equation of an element which satisfies Ohm's law, like a conductor with some finite conductivity. So, these elements, of course, a resistor is effectively governed by an algebraic equation which is Ohm's law. Now, these circuit elements are idealized in the sense that in an inductor we at least when we describe it by the equation V is equal to L di by dt, and where this equation holds, we assume that the electrical fields within the inductor are negligible, and similarly in a capacitor we do not consider an ideal capacitor, we do not consider the effect of the magnetic fields within the capacitor. So, now of course, we will string together these components and form what is known as a circuit, and then the circuits will be governed by the Kirchhoff voltage and current rules, which are in fact derived, which are derivable under certain circumstances from Maxwell's equations, and this is something we have discussed in the earlier lectures. So, we will directly plunge into trying to understand some simple circuit behavior. The first circuit behavior is a simple RL circuit, and if you look at an RL circuit, suppose this is a voltage source and this is connected to an RL circuit. Now, what we will do is analyze some simple circuits of this kind and also bring out some subtle aspects which may have escaped you when you first did this in either high school or your first year engineering courses or first year science courses. Now, in this circuit, this is a circuit, if we apply Kirchhoff's voltage rule or Kirchhoff voltage law, we will get the equation by Kirchhoff voltage law V minus, suppose this is I R, which is the voltage drop, and the voltage drop L di by dt. So, these are idealized elements, and we of course, here we are taking a loop, we will neglect the effect of possible change of flux through this loop. So, we will not take into account that, we will assume that it is small because the flux, either the flux levels are small or the rates of change are very small. So, in that case Kirchhoff voltage law applies in the way I have written it down, and this is equal to 0. So, what we can write it as a differential equation, L di by dt is equal to minus IR plus V, or in other words di by dt is equal to minus R by Li plus 1 by Lv. We can also write it in a slightly roundabout fashion. For example, we know that the inductor current in fact is actually produces the flux within the inductor. So, inductor is like a I will just show one coil. The current through the inductor causes a flux, and that flux, the rate of change of flux causes E dot dl in this path, and therefore, the voltage across this, that is the potential of A with respect to B outside we assume there are no magnetic fields, the potential of A with respect to B is equal to L di by dt. But we can write this equation also as d psi by dt is equal to minus IR plus V, and I is equal to a function of psi, or in other words psi is a function of I. So, what this is another alternative way of writing it. Psi denotes the flux through this single coil of wire, or in case you got multiple turns, n into the amount of flux going through the wire. So, that is flux, I mean of course is B dot ds integrated over this surface. So, what we an alternative way of writing is, you can write this as L di by dt, or di by dt is equal to minus R by Li plus V by L, or you can write it in terms of the flux or flux linked in case they are a number of turns is equal to minus R I plus V, and psi I is equal to a function of psi. Now, of course, since if you assume that the flux through this is a linear function of current, which it normally will be in case there is free space. Remember that there is a constant of proportionality called mu naught, which relates the current and the flux. Which appears in the current flux equation, and that is simply a constant. So, we in fact expect that I is equal to psi by L, in which case we come back to this equation. We will also of course, in case you have got this is wound on a ferromagnetic material like steel, magnetic steel like this. Here I have shown several turns. You will find that the flux is no longer linear, because instead of mu naught you have got mu, you take into account the ferromagnetic material properties. We discussed this some time ago. Instead of using mu naught, we will use mu is equal to mu naught mu r to take into account the magnetic the atomic currents which are there, which actually enhance the field for a given external current. So, what we do is this, but this mu is normally not a constant, this mu r is not a constant. It usually for a ferromagnetic material is of the order of 1000 or several thousand, and but if the flux level increases in the core, the value of mu r in fact saturates, in the sense that mu naught in fact is, there is no linearity. In fact, mu is a function of the flux level, and if the flux level increases beyond a point, then mu r actually starts dropping. So, this is an interesting point, but in case you have got a linear core, I can be written as psi by L, and you are back to square one, that is this equation. So, you can use this equation or you can use this equation. Let us use this equation, assuming that the inductor is an ideal one and is linear, that is mu r does not change with the flux level. Then essentially di by dt is equal to minus r by L I plus V by L is an example of a differential equation, and if you want to solve a differential equation dx by dt is equal to Ax plus Bu, what is the solution? In case B is 0, that is dx by dt is equal to Ax, you know that the solution to this is equal to minus plus Ax into x of 0. This is the solution of this simple differential equation. What happens in case you have got an additional input? I will give you the expression without proving it. I am sorry, this should be At, this should be At. Now, this is you can verify that at t is equal to 0, x0 is equal to x0. So, this is a self consistent equation, and also the derivative of xt will come out, will satisfy this equation. In case you are having the input dx by dt is equal to Ax plus Bu, in that case the solution is e raised to At x of 0 plus what is known as a convolution integral. So, this is 0 to t e raised to a t minus tau into b u tau, u is could be a function of time, into d tau. Remember that the integration is over the variable tau, not t. So, it is e raised to a t minus tau b u tau d tau. So, if you want to apply this, I am not proving to you here, but this you can verify by taking the derivative of x of t, which is an interesting exercise because the t appears as the limit here. So, it is a bit of a nice exercise to try to show that dx by dt satisfies this equation. And of course, if t is equal to 0, this will be 0 to 0. So, this is 0 and you will get x0 is equal to x0, which is of course self consistent. So, this equation appears to be right as far as the initial condition is concerned, but you can verify that this is the response of this, rather this equation satisfies this differential equation. So, if you want to apply this to say a system like this which is excited by a DC voltage source. So, I will just draw this. So, we got an RL circuit and you assume that you switch on this a DC source onto it. If you do that, you will find that the solution therefore will be, this is V, the solution will come out to be I of t is equal to e raised to minus r by L t into I0, we will just write it as I0, but in this circuit if nothing else was connected before this switch was closed, the current also would be 0. So, I of 0 would be 0 plus, but we will just write down this expression nonetheless, 0 to t e raised to minus r by L t minus tau into B into u tau is simply a DC voltage source. So, V divide B will be 1 by L and d tau. So, if you actually evaluate this expression, this will come out to be I of t is equal to e raised to minus r by L t I0 plus this expression 0 to t, I will just rewrite it, minus r by L t minus tau V by L d tau. Now, if you just look at this part, you will find that since the integration variable is tau, you can actually take out this. So, this will come out to be e raised to minus r by L t, you can take out that expression here, 0 to t e raised to r by L tau V by L d tau. So, this is the expression here. So, this will lead to, this leads to e raised to minus r by L t into, since this is a constant, V will just come out of this, L will come out of this, e raised to minus r by L tau, if you integrate you will get e raised to r by L tau into 1 upon r by L, which is nothing but 1 upon r by L would be this, and this is integrated over 0 to t. So, what you will get after that would be e raised to minus r by L t, we will just work it out, you will get, yes, you will get 1, e raised to r by L t minus 1 into L by r, L and L will cancel. So, what you will get finally would be, this will lead to V by r 1 minus e raised to minus r by L t. So, what your final expression for t therefore is e raised to minus r by L t I0 plus V by r 1 minus e minus r by L t. Now, note that in this circuit you can actually split this into two parts. One is e raised to minus r by L t into I0 plus V by r or minus V by r into e raised to minus r by L t, and the other expression which does not contain this e by r, this is simply V by r. And if you notice that as t tends to infinity, because this is a negative number, these terms will tend to 0, and this is in fact called the natural response of this circuit. This is in fact the steady state response which remains after the natural response has died down. In fact, if you look at this circuit, in steady state means all the derivatives become equal to 0, you will find that the current will simply be I is equal to V by R. So, this is in fact the steady state current. So, your response looks like this. In case you have a sinusoidal input, in case you had a sinusoidal input, that is di by dt is equal to minus r by L I plus V, where V is not a DC but sinusoid, that is V is equal to Vm sin omega t. In that case what happens? Well, the integration becomes a bit more complicated. I will just show you how it will look like. So, I of t will be e raised to minus r by L t I 0 plus 0 to t e raised to minus r by L t minus tau into now Vm sin omega tau d tau divided by L. So, now you have got this integration becomes a bit more complicated, because you will have to integrate e raised to minus r by L t tau into sin omega tau. So, this is a bit of a mathematical exercise. I will directly write down the solution. There are standard formulae for e raised to ax sin bx dx, the integration. So, you can try to look back on your 12th standard mathematics to actually find out this integration, but I will not do that here. I will directly write down the expression. The expression turns out to be I of t is equal to e raised to minus r by L t I 0 plus you will get a term which is equal to Vm by square root of r square plus omega square L square into sin omega t minus phi, I will tell you what this phi is, plus Vm by root of r square plus omega square L square. This is an interesting exercise in itself to get this expression, but we will not do this here. Sin phi into e raised to minus r by L t. So, what you get is again a term which is independent of e raised to minus r by L t, and certain terms which are in fact dependent or multiplied by e raised to minus r by L t. Of course, I have not defined what phi is. Phi turns out to be equal to phi is equal to tan inverse omega L by r. So, what we get is a expression for current. Again, if you look at the expression, it is a sum of a natural transient which dies down eventually. In fact, as t tends to infinity, these terms here will die out, and what remains is a sinusoid, but with a phase shift and some scaling. And interestingly, the scaling comes out to be square root of r square plus omega square L square. Now, this in fact is what is known as the sinusoidal steady state response. This is the steady state response which you will get after all the natural transients have died down. Of course, remember that there are natural transients, and you will in fact, if you switch on this circuit at time t is equal to 0, you will find that there is some exponentially decaying terms as well as the sinusoidal steady state term. Once these things die out, you are left with the sinusoidal steady state. So, this is something which you probably have done before, but just to refresh your memory, I have just done this again. Now, of course, what does this mean? I mean, these look like complicated mathematical expressions, but if you assume I 0 is equal to 0, in that case, suppose I switch this Vm sin omega t at time t is equal to 0, this is voltage. What you find is this, the response is a summation of an exponentially decaying response plus, so this is voltage versus time, but what is the current response going to be? You have one term which is simply saying which is Vm sin phi, if you look at what it was here, this term which is simply exponentially decaying. So, depending on this value of phi, let us say it is if you assume a certain, this is say 45 degrees, then this will be 1 by root 2. Suppose phi is 45 degree, depends on the values of L, R and omega. So, suppose this, then what you will get is a term which is like this, this starts as Vm by root 2 divided by r square, square root of r square plus omega square, which dies down with time, and the rate of decay of course is dependent on the value of r by L. In fact, if you got a term like this, this practically becomes 0 after t becomes about 4 to 5 times L by R. So, this is one important point. So, suppose L by R is 1 second, around 5 seconds you will find this dying down. Okay. So, this is one of the points which you should note. The frequency of course omega is equal to 2 pi divided by t, where t is the period of this. This is the first component of, if you assume I0 is equal to 0, this is the component of the natural response, assuming that phi is equal to 45 degrees, and this will be then equal to Vm by root 2 1 upon root of r square plus omega square L square. You also have what is known as the sinusoidal steady state current, which is going to be lagging because of the fact that this is sin omega t minus phi. Lag, say of 45 degrees would mean that it would be lagged and scaled by root of r square. So, it will be like this. So, that this waveform lags this waveform by 45 degrees. So, you will find that well, it is not very well drawn to scale, but this is roughly 45 degrees, not drawn to scale. So, what you will find is that your response of current is this plus this. So, what you get here is if I is 0 is equal to 0, you will find that your current is in fact having a DC offset and it decays, and then you come into sinusoidal steady state, and the voltage of course is like this, sorry, and you will find the current is lagging by this angle phi. I have not drawn it very well, this would be 45 degrees as per our example. So, in steady state of course this voltage and current are relationship is simply given by root of r square, the current is scaled by the voltage, is scaled by the term root of r square plus omega square L square. So, this is how you expect the sinusoidal steady state response of an RL circuit to be. Now, if you look at you can in fact do this numerically also. For example, you could numerically integrate the equations. For example, we can consider the numerical integration of dx by dt. If you have given a system of equations dx by dt is equal to fxu, you can actually discretize it using forward Euler method. FEM is really here is an acronym for forward Euler method. You assume that this differentiation is done approximately. So, dx by dt is replaced by xk plus 1 minus xk by h, where h is a very small time interval, we call it time step, and f is in fact evaluated at the kth interval. So, in fact if you know the value of x and u at the kth instant, then you can easily compute what is the value at the k plus 1th instant. In fact, what we call here is x of k is nothing but x evaluated at the instant k h. Okay. So, yeah, this is what I meant, xk is equal to k h. So, this x underscore k means the value of xk evaluated at k h. This kind of discretization is required because you find that you want to do this on a computer. So, what you find here is of course because it is discretized, you can actually do this as a kind of a algorithm on a computer, and I will just show you how you can do it. Of course, the value of h should be chosen appropriately. This finite Euler method is a method of numerical integration. In fact, it does not have very nice numerical properties, in the sense that if you want to simulate systems using this method, usually you have to choose a very small time step, and if we do not do that, we end up with large errors in the simulation. So, we have to choose our h quite small, but since this is a very simple method, we will quickly show you how to do the integration. So, this is a program in Scilab. So, we do that slowly, right, begin. So, what we are going to do is a simple RL circuit with a DC input. We can vary the switching instant or the values of R and L and so on. So, first thing is we will just do the base simulation with the values R is equal to 30 and L is equal to 30 ohm and L is equal to 60 millihenry. Pi is of course what we know, and the time step we choose is a very small one. This is 10 microseconds. Whether we need such a large time step, small time step is a question we can try to answer, or you can think over it. In fact, the time constant of this circuit is L by R, which is in fact 60 millihenry divided by 30 is simply 20 milliseconds. So, this h is chosen to be much lower than that. Perhaps we can work with larger value of h. That will make our simulation a bit faster, because we can have fewer time steps in 0.1 seconds. So, what we are doing here is a circuit which is DC with a DC input, and we are switching the DC input at time t is equal to 0, and using that we can actually see if we get the kind of response we expect to get. Remember, the input here is DC, not AC. V naught is taken to be DC with a value of 9.35. Why we are taking this value is something I will try to tell you a bit later. It is a value, it is 9.35 volts, and it is a constant value. So, that is why for all time steps it has got the same value. The initial value of current is 0 in the circuit, and what we do is now numerically obtain the value of I by applying Euler method to this system. So, I will just quickly get you how we got this equation. di by dt is equal to minus R by L I plus V by L. So, this can be written as I k plus 1 minus I k by h is equal to minus, this is f of x, and u is v, which is a constant, I k, which is essentially the function evaluated. This is a constant, so V k is just a constant. So, we will get I k plus 1 is equal to I k plus minus R h by L I k plus V k by L. So, if I know the value of I k, I can get the value of I k plus 1. So, what we will do is we will actually obtain the I for these values. This is called numerical integration, and what this is something which my student here will actually run this simulation, and then we will get back to it. So, what we have here is this expression here, which is going to be evaluated using a simple computer program which is written in Scilab. So, what we will do is of course plot this, and we will plot both current and voltage on the same plot. Because current we expect it to be a bit low, I have scaled the current by 10. So, let us just plot this and see. Yeah, maybe you should, yeah. So, actually if you look at the current and voltage, you will be able to see that this is the voltage, the red is voltage, and this is current, but it is of course scaled by, it is multiplied by 10. So, of course, in steady state we know that in the RL circuit the current is V by R. What you are getting here is the current is 3.33 approximately, and of course, this is multiplied by 10. So, actually the current is 0.333, and this is what we get because we are using a resistance of 30 ohm. Well, this value 3.33 is not correct. We have got 30 ohm and a voltage of 9.35. So, 9.35 divided by 30 is the actual current flowing through the resistance. This has been scaled by 10 times. So, you know you get 10 times this. So, this is all very consistent, and you see this current going to a value of uh, the steady state value, and the natural transient which you see is actually the one there, yeah. So, this is the natural transient. You do not directly go to the DC value, the steady state value, you have got initially a natural transient. So, we have seen this before. This is the response which we had computed. I will just show that to you again. Yeah, this is the response. So, you got V by R and this V is 9.35, R is 30, and this is the natural response, this is the steady state response. So, what you get in fact is a waveform which is, this is V by R is of course a constant, this is the first thing, plus the natural transient. The natural transient is minus V by R. So, this is in fact like this. So, when you add these two, you will get a response which is like this, and the final value of course is V by R. So, this is not surprising what you are getting, and this is of course the novelty is of course that we have numerically integrated to get this. One or two important points before you we move on. Numerical integration here has been done by forward Euler method with a fairly small time step. You can actually experiment by increasing the time step, and one of the things you can expect is that the solution will become more inaccurate. The transient especially will become more inaccurate when this H starts approaching the time constant of this circuit, which is L by R. So, this is something which you can try to experiment with yourself. So, we will go next to the RL circuit with a sinusoidal input. So, now let us just look at a program which does exactly that. We will of course be numerically integrating this system. What we have here is a program. We are going to use an RL circuit, but now if you come down, go slowly, this is actually having a sinusoidal input. Earlier we had DC 9.35 volts, but now you have got a sinusoidal input. Now, if you actually do this numerical integration, the only difference here is, this is remember numerical integration. So, we are not directly writing any formula, we are just numerically integrating it. This voltage here is not constant, but it will actually change sample by sample, okay, or time step by time step. If you do this simulation, what you will get is this, the response will turn out to be, can we just show it? Yeah. So, what you have here, the red is the voltage and the blue is the current, and what you notice here is of course that there is a exponential decaying component, which is a natural component, and as you reach steady state, the blue, that is the blue waveform which is the current, lags the voltage. In fact, the lag is equal to tan inverse omega into 60 millihenry divided by 30 ohms. So, this you can verify that this is in fact equal to this lag. If we actually change the value of R or L, there are two things which will happen. For example, if I make R to be a value say 100, in that case you will find first thing is that the natural transient will die out faster because the time constant of the circuit will reduce, and the second thing is of course the phase shift between the voltage and the current will also change, because phi is equal to tan inverse omega L by R. So, can we do that? So, what we will do is change the values of R. This is in this case 1.5 ohm, so not 30 ohm. In this simulation it is taken as 1.5 ohm. We will multiply it by thrice, say you just make it 4.5 ohm. So, now the time constant is reduced. Yeah. So, can we just see what the response is going to be? Yeah, first thing you notice is of course that your decay is faster, and the other thing is the lag would have slightly reduced. Now, we did not note down what the lag is, but can we do that roughly? Can we just find out how much this lag is? Not exactly, but at least have a mental picture of it. Yeah, so if you look at this, this is roughly you know, one point, no, if you look at the phase shift is roughly 0.005, roughly 0.005 seconds, that is the phase, the time delay. If we reduce the value of R to its old, so what is the value? We better note it down, 0.005 seconds, yes. Let us go to get back this value to 1.5, yeah. And of course, you see that the rate of decay is much slower in this case, and very marginally you see that now in fact it is 0.005, in fact the lag is still almost the same, that is because you are actually omega L is practically swamping the value of R. So in the earlier case, omega L by R was 2 into pi into 50 into L. L is nothing but this is a 50 hertz, incidentally omega is the radian frequency, something I did not mention earlier, and 50 hertz is in fact the frequency in hertz. This is equal to 60 millihenry divided by R. In the earlier case it was 1.5, now it is 4.5. So in case 1, case 2, it is 2 pi into 50 into 60 into 10 raised to minus 3 divided by 4.5. So Kaustav is doing calculation and he will tell us shortly what these values will be. In case 1 this is equal to tan phi, that is in case 2 this is equal to tan phi 2. So phi 1 turns out to be equal to 85 and phi 2 is equal to 76. So this difference is not much, it is not perceptible by us very easily, and of course because of that you know, this is almost a quarter of a cycle, so that is why you get 0.05. So in fact increasing resistance by 3 times does not of course increase change phi 2 to that extent. In fact, since omega L is much larger than 1.5, your angle phi 1 is near 90 degrees. Of course, you could keep on playing around with these values of L and R. For example, if you made this 10.5 or just 10. Now of course, you should see a perceptible difference in what you see. Of course, the natural transient dies down very fast, and now your angle phase difference will be certainly less than perceptibly less than 0.05 seconds, which is indeed true. In fact, this comes out to be almost 3/4 of 0.05 seconds. So this kind of you know, behavior is absolutely as predicted. The time step of this simulation is taken to be you know 10 microseconds, and we normally, at least with these small time steps, we seems to be getting a reasonably accurate answer. But you can of course experiment with larger time steps, that is larger h, and see what effect it has on the error. Now what we will do next is you know one of the takeaways from all this is that this is how your system behaves when you are going to have an RL circuit suddenly switched on to a source. Now interestingly enough, what we will do is I will try out a simple experiment here. First, not the numerical, we will first do a numerical experiment before we do an actual experiment. Let us just get back to the Scilab program. Yeah. So what we have here is 10 ohm, we will just make this back to 1.5 ohm. Yeah. And what we will do is that instead of V sin omega t, we will do V sin omega t plus say 40 degrees or 30 degrees. We can just do it plus 45 degrees. So now what we will do is this is pi by 4 you put 45 degrees. Yeah. So what we have here now is, as we redo the simulation, one of the things which we need, of course, to have a bit of photographic memory to remember how the earlier simulation looked like. So what we will do here is we will just try out various values. Right now we almost can't perceive what the difference is between the earlier simulation and this one. So let us do one more thing. Let us change that angle to 90 degrees and look at the kind of response we got. What do you notice? One of the things is, if you start somewhere near you switch on a voltage source which is now sin omega t plus 90 degrees, the natural transient has in fact shrunk very significantly. If we in fact make the the source, we switch on the source which is V sin omega t plus phi, where phi is omega L by R, we will have no natural transient. So can we just so we can actually control the natural transient by the instant at which we switch, which is an interesting point. In fact, it is something which is used in power systems when we want to reduce the natural transients associated with switching. So the instant of switching with respect to the waveform, say here in this case the voltage waveform, is in fact something which can change the transient. So what we are going to do is, we are going to make the voltage source be equal to omega t plus phi, where phi is equal to omega L bar. In this case, you will find that you practically have no natural transient, the system simply goes into steady state. Okay. So you can actually change the natural transient amount of natural transient which you see by adjusting the time instant of switching. In fact, if you make you can we just close that and make it minus a tan, suppose instead of, so I choose another instant on the sine wave where I switch. In this case you get another kind of transient, but so this kind of you can play around with this instant of switching on the sine wave. Although I am switching at t is equal to 0, I am actually shifting the voltage waveform. So the instant on the voltage waveform in which at which I switch changes the amount of natural transient you see. Now what we will do now is observe the kind of responses we get in a realistic experiment, where we will first look at RL transient of a simple RL circuit in a real RL circuit, that is using real life components. In this case you have got a rheostat which is the value is adjusted, so it is 30 ohm. We will actually redo the DC transients, the example which we did some time ago, with R is equal to 30, L is equal to 60 millihenry. The inductor itself has got a bit of resistance, so we may have to slightly do a bit of adjustment there. Can you go to the next slide? So this is essentially what we are going to do. The voltage is a battery of 9.35, that explains why I chose the value of 9.35 in my simulation as well. This R of the rheostat is 30 ohm, whereas the inductor is 60 millihenry. This is the kind of values we use in our simulation as well. The inductor also has got some resistance, so we can expect that there will be some difference between what we see here and what we get, what we got in the simulation. So there is a voltage probe and a switch which we will switch on, and we will observe the waveform using a current probe, and what we will do is, of course, find out V and I and plot it. We may of course scale the voltage and current so that they are visible on the same scale on the oscilloscope. So we will so what is going to be done is, for some reason, so he switched on this voltage, and we have actually measured the voltage across uh, the resistor and the voltage, the current. So, current V is, can you just show what is V? If you go back, we will see how the voltage probe has got connected. So, what we have connected this voltage probe across is, so he is connecting the voltage probe across the one terminal of the resistance and the battery. The battery actually is 9.35 volts, but what we are measuring in fact is the voltage after the switch. So, in fact, just to make things a bit clearer, because there is some interesting subtle point which I want to explain here. So, we got this battery which is 9.35, and this in fact what is being measured is the voltage not across the resistor, but this point and this point, and the current is of course this current here. So, what you expect is of course that if I switch this on, your voltage will be like this and the current would be like this, which is in fact it is. If you look at the kind of waveforms which we get is in fact consistent with this, but there is a small interesting subtle point which you would have noticed is that the voltage is not a step, but in fact the voltage actually drops. In fact, what we see here, if you run the mouse over this, we will see in fact the voltage is 9.35 to begin with, but in fact it drops down a bit. What we expect was this, and what we get is this. So, this voltage waveform is not exactly a step, but you in fact find the voltage slightly dipping, because this battery is again not an ideal source. The thing is that when we draw more current from the battery, the voltage across the which we get across the battery is actually decreasing. So, as the current rises, the current is rising in fact here, the voltage in fact drops. So, this really shows that this is not an ideal voltage source. In fact, the voltage drops. The current which you can expect in steady state is 9.35 divided by 30 ohm. So, that is a value which loads the battery very significantly, and the voltage actually drops down. So, this is one interesting outcome of this experiment, where you find that the voltage of the battery slightly dips when the current increases. So, we move on next to another experiment, which is the sinusoidal input. When you apply a sinusoidal input, the experiment will be shortly shown to you. In fact, now you have got a AC voltage, and it is practically a similar kind of setup. We will increase the voltage to using a variac, something which we will discuss a bit later. It is a kind of an it's in fact a auto transformer. Yeah, let it just run. So, this is 1.5 ohm and you have got a 60 millihenry inductor. This inductor itself has some resistance which has not been accounted for, but that will affect our results as well. So, if you try to switch here this source, you will find that now the behavior is as predicted. So, this is 7 volts, but this is the RMS value. So, 7 into root 2 is approximately the voltage which you will get, and now he will switch this on. Yeah. So, the instant at which this switch is switched on is almost random, because your hand you are just switching it on, but you are not really knowing exactly at what point on the sine wave you are on. So, we will actually try to do experiments with varying switch instants. So, you see the DC offset which is there. If you wait for some time and go back, you will also find some interesting things, like there seems to be a small parasitic kind of spike there in the beginning, and if you actually change the instant at which you switch, you will find that the DC offset actually changes. The current is yellow and the blue is in fact the voltage. You will find that at the instant of switching, because of the switch itself as well as some high parasitics which you have not modeled, you do get some high frequency transients, but not in this this specific figure. So, you will find this DC offset and this steady state, and if you switch at various instants, the DC offset changes. Of course, the steady state with respect to the voltage waveform will look identical whatever the time of switching will be. So, this is in fact consistent with what we have done in theory. The things to note, of course, is the important thing is that when you do switch, you do sometimes get a bit of a spike in the beginning in the voltage. That is probably due to the switch. It is not an ideal switch, it is not something which is suddenly becoming it does not instantaneously switch. And the second thing is that there are some parasitics which we are not modeled in this circuit. Remember that all the circuit is a loop, and the loop also has got a stray inductance, an aspect which we have discussed earlier in the previous lecture. So, we now move on to an interesting aspect, which is relating to a practical system in which this L is not a constant. In fact, we do not treat it as if it is a constant, but it is in fact a function of the flux. I had discussed this some time ago when I had discussed this. We assume that I is equal to the flux linked. Flux linked is nothing but the number of turns into the flux. The flux is of course B dot ds integrated over the surface, which is in fact bounded by the curve in which we measure E dot dl, and therefore, this if we assume that you have got a linear core, that is the material here is free space, then of course, we have to use the value of mu naught to get the relationship between B and I using Ampere Maxwell's equation. Now, what I mentioned some time back was normally we use a ferromagnetic core, and because the ferromagnetic core has got a relative permeability, that happens because for a given external current through this winding, the flux in the core is usually, a ferromagnetic core is much more than what you would expect in free space, because this ferromagnetic material itself has got atomic magnets, you can say, which kind of get aligned and enhance the flux in the core. So, we take this into account in a very approximate way by using mu instead of mu naught, and mu is in fact mu naught into mu r, and mu r is a large value. Usually for steels it could be of the order of 1000 or more. So, but one of the important things which I mentioned some time back is that if mu r is constant, nothing really changes except that the flux is much more compared to the free space value, but otherwise everything is the same. But one peculiarity with real life with a real life core is that once you if the flux level increases in the core, mu r in fact starts dropping. That is, if you look at the flux level in an inductor, if you have got an inductor and if this is a flux linked, is nothing but number of turns into the flux. If you have got one turn, it will be just the flux. If you look at, if the current increases, if you have got free space, then this psi I relationship is linear, and this really this curve depends on mu naught, which is constant, and the geometry of this, including the area of this and so on. And what we see, in case you got a ferromagnetic core, suppose I have got a toroidal core around toroidal core, and this is actually in fact wound around a toroidal core. In that case, what we find is this psi is much higher. So, you got something like this, but it kind of saturates after a while. So, your phi I relationship, the slope of this is much larger, almost could be as high as 1000 or 10,000, tens of thousands high, tens of thousand times higher than the slope of this. But as the flux level increases, there is a what is known as a saturation value of flux density. Flux and flux density are equivalent, because in this case, because we are not changing the geometry of this. So, there is a value of flux linked which kind of saturates, which is because of the fact that the flux density also saturates in a ferromagnetic material. Now, what is the implication of this? Now, because this is happening, it is not correct to use a constant value of L. So, we cannot write di by dt is equal to minus IR by L plus V by L with L constant. What we will have to, because now the flux linked is in fact I is a nonlinear function of the flux linked, or vice versa. The flux linked is a nonlinear function of I, and I is not simply psi divided by L. So, in fact, the equations, these equations can be written as d psi by dt is equal to minus IR plus V, where I is equal to psi by L, but this L is not a constant, but it depends on the value of the flux at a given point. So, in fact, I could, for example, say the equations are these, and psi is not I is not psi by L, but it is equal to psi by L, where L is a constant, but you multiply it by some nonlinear function. So, what we can do, for example, is have a nonlinear function which matches the kind of characteristics we have. So, for example, in this case will take, let us take a nonlinear function. So, what I will do is I will take this as psi by psi 0, I will rewrite this because this is a bit messy, by 2, and this multiplication constant which I will take here is equal to 2. Okay. So, what I will do is I will make this relationship nonlinear, that is current is not equal to psi by L, where L is a constant, but current is equal to psi by L. I will rewrite this because it is quite not written very clearly. So, if the flux magnitude of the flux increases, this in fact the amount of current required for a certain value of psi increases much in a nonlinear fashion. So, this is what is known as, this is a function which I have chosen. It is not actually a replica of real life real life characteristic, but it is just giving you a nonlinear function which kind of mimics the fact that this current is a nonlinear function of psi. So, what you notice in this nonlinearity is that if psi becomes much as psi by psi 0 becomes larger, the change in the current for a given amount of for increasing flux is much higher at larger psi. So, this kind of mimics the saturation of of a ferromagnetic core, and what we will do is redo this simulation. So, what you notice here is what I have replaced here is this function. So, I have replaced I by the function shown here. Earlier I had psi by L as I, or I is equal to Li is equal to psi. So, I had written down the differential equation in terms of I, which is okay. But now what I have done is I have rewritten the differential equation, but I have introduced this nonlinearity. So, this I here is replaced by this. So, instead of simply by having R by L, we will in fact have an equation in psi. So, what we do is redo this simulation with psi as the variable, and the psi I relationship we take as nonlinear, and what we do effectively is compute psi, and of course, once you compute psi you can also get I. So, what we redo this simulation, and let us see what we get. We are going to switch on at time t is equal to 0, and the voltage source is Vm sin omega t, and let us see what we get. So, what we see here is that we are getting a curve which looks somewhat different. So, now the response is quite different. So, I have plotted IL, I actually computed phi and recalculated IL, and what we notice is because you have taken a nonlinear core, the response of the current looks quite different. In fact, it is not sinusoidal, it is in fact you find that it has got the voltage is sinusoidal, but the blue curve which is the current is non-sinusoidal, it is kind of peaky. The reason of course is because the flux is the flux linked is approximately the integral of the voltage, and although that is sinusoidal, the current is not sinusoidal because flux and current have a nonlinear relationship. So, you find a kind of a peaky nature, it is a kind of peak which you get somewhere at the, because you need much more current to set up the same amount of flux because of the nonlinearity. Okay. So, this is a interesting aspect about a nonlinear core. The thing is that you in steady state you get a kind of a non-sinusoidal waveform. It has got harmonics, although it is periodic, it seems it is not sinusoidal, and the current kind of is a very peaky, of a very peaky nature. So, can we just do one more interesting thing is go up, and what we will do is just to let this transient be a bit more prominent, we will make this resistance as reduce it by 1 point from 1.5 ohm we make it 0.15 ohm. So, let us see what happens. So, what we notice is of course that we get a much larger current, and this peaky nature is very prominent, and you also, because R is reduced, it takes a long time for this to settle down. And in case because of the fact that you have got this nonlinearity, the current is almost scaled, this is almost 10 ampere, more than around 20 ampere the peak value. The current is scaled, it is multiplied by 10 here. So, you get but it may not be very visible to you, but roughly it is around 18 ampere. Now, in case I did not have this nonlinearity, can we just go back, and what we will do is multiply, we will just cancel out this nonlinearity by multiplying it by 0, and also there, yeah. And if you rerun this program, the current is much less, in fact it is almost 10 times less. Okay. So, what you find here is more than 10 times less. The current is in fact roughly 1 ampere, it is scaled, it is multiplied by 10. So, what you are seeing is a peak of 10 ampere is actually 1 ampere, and you have got a decaying offset. But the nature of the decaying offset, in fact you look at the steady state, eventually the offset dies down, but eventually it settles down to a sinusoid. So, if you got nonlinearity like the one shown here, you are likely to get a very peaky kind of nature. Now, what we will do is we will actually do this with a real life transformer. In fact, it is I use the word transformer, which is in fact a mutually coupled circuit, but in fact the transformer, this particular transformer has two coils, the primary and the secondary. They are mutually coupled, but I will keep the one of the coils open. So, for all practical purposes, since no current is going to flow in the second coil, this is actually like a single winding inductor. What we are going to do is apply a voltage which is equal to 230 volts or nearabouts on this inductor. I call it an inductor because the secondary is kept open. And what we are going to do, for example, it is being shown that the inductor is open circuited, and this is in fact connected to the laboratory power supply, which is in fact 230 volts, and what we are going to do is just switch it on at some instant. And remember, can we pause for a minute? Remember, this inductor is a real life inductor. The voltages applied are going to be quite large. In fact, the entire voltage power 20 to 230 volts is going to be applied to this. In the earlier example, we were applying only 10 volts. In fact, since the voltage was low, the inductor was practically a linear one in the earlier case. Now, what we are going to take is a inductor or a transformer with the secondary open, which is equivalent to an inductor on the primary side. So, you are going to excite a coil, an inductor with 230 volts, which is also the rating of the inductor. Now, when you design an inductor, normally you will design it so that it does not saturate when you apply 230 volts. It may have saturated a bit, but it may be starting to saturate, but it is not fully saturated. But because of the DC transient, the transient transients which are there, you may actually have DC offsets in the fluxes, and that may actually cause it to saturate. And because of this, we enter the nonlinear region, and we should see waveforms which of the kind which we have seen in our simulation. So, let us just see if this actually happens. So, that is the voltage, and you also have the current, and we are going to switch this on. We are going to trigger the oscilloscope, so it kind of picks up. So, what you notice is the current. Now, this current is, you see this peaky nature, the kind of thing which we observed in the simulation as well. So, what you will find is that the current, it is extremely high peak compared to what we get in the steady state. The steady state waveform, the magnitude is low, but when you switch it on, the current is almost 4 to 5 times the steady state waveform. In fact, what you find is that eventually when the offset, when the DC offset dies down, the current settles to a reasonably low value. But even then, you will find that the current waveform is not a linear one. Can we just, is not a sinusoidal. Okay, this is just showing how the initial current is. We see the peaky nature, and this is the steady state waveform which you get. Actually, he has increased the current scale, but what you notice is that the waveform is not linear. It is in fact having this peaky nature. It is not sinusoidal. One interesting thing is that the voltage applied also does not seem to be sinusoidal. That is because the nature of the laboratory power supply is not very sinusoidal. So, that is another issue which we shall tackle a bit later. But just not to confuse these 2 points, the voltage itself here is non-sinusoidal, but what I wanted to show you here is that the current nature is peaky, okay, and this would in fact be true even if the voltage were actually sinusoidal. So, this kind of concludes our discussion of the transients with RL, RLC, etc. Remember that the DC, this, if you in case have saturation, the transients can be quite very significant. In fact, the transient waveform, the DC offsets in the current can be very large. The reason is that during the transient, the flux levels in the core can be high because of the decaying DC offset, and to create those flux levels in a nonlinear core requires a large amount of current. So, that is called this brings out the issue of saturation of ferromagnetic cores, and so the effect of saturation and the transient is to effectively have a very large inrush current, and this is something which is observed in transformers. Transformer inrush is a bit of a something which people have been worried about, because sometimes this kind of fools the protection system. So, if you have got a very large current at the beginning, sometimes the protection system of the transformer may think that there is a fault. Now, what is the protection system is not something which I have discussed with you, but you can imagine it as some sensor which is monitoring these currents and ensuring that there is no fault in the transformer, there is no short circuit which is causing a large current. All these aspects will be discussed like short circuits a bit later, but essentially what we want to say is that in a RL or RC circuit or a RLC circuit, you have got this natural transient and a steady state. In case you have got sinusoids, you have got a sinusoidal steady state. These transients which you see in the presence of saturation in an inductor can result in very large currents, which in fact can sometimes be very large, in the sense that the steady state current and the inrush current can be, there can be almost an order of magnitude between them. So, this is essentially what I wanted to show here. Yeah. So, in the next class I will discuss another interesting circuit, which is a RLC circuit, and we look at the nature of natural transients in an RLC circuit, and thereafter we shall try to study this. We shall focus not on the natural transients, but on the sinusoidal steady state response, and related to the sinusoidal steady state response is what is known as the general frequency response of circuits as a function of frequency. And it is a useful exercise to revisit this, because this is related to the frequency response of such circuits. In fact, is related to some of the signal processing things which we do, signal processing analytics which we do, including filtering and so on. So, this is something we will cover in the next lecture.